You know how to calculate an average, right? Of course you do. But what if I told you that simple number is actually hiding the most interesting parts of your data story? Well, in this explainer, we're going to pull back the curtain and uncover the true shape and personality of data, going way beyond the basics. So, you've probably used the mean, median, and mode a million times to find the center of your data. But those numbers, they're really just the first chapter of the book. They don't tell you anything about the data's personality, its lopsidedness, or its potential for some really extreme surprises. To get that full story, we have to understand its shape. Alright, so here's our game plan. First, we'll break down what statistical moments even are. Then we'll do a quick flyby of the two you're probably already familiar with. After that, we're diving deep into skewness and especially kurtosis, because that's where the real juicy insights about your data are hiding. So what are statistical moments? The best way to think about them is like a personality profile for your data set. Seriously, they're a set of measurements that, when you put them all together, give you this rich, multi-dimensional picture of what your data is really like. Okay, so the textbook definition is that moments are quantitative measures of a distribution's shape. But let's make that real. If your mean is just the first single brushstroke on a canvas, then each new moment we add is another layer of detail, another color, revealing a way more complete picture of how your data is actually laid out. Now, the first four moments are the most common ones, and they're super powerful. The first moment, the mean, that just finds the center. The second, variance, tells us about the spread. The third, skewness, shows us if it's lopsided. And the fourth, kurtosis, well, that describes the tailedness. And as we're about to see, this is our secret weapon for understanding the risk of extreme outliers. Alright, let's start with the two you already know, even if you don't call them moments. These give us our basic bearings. They tell us where the center of our data is and how spread out it is. So, the first moment is the mean, the good old average. It's basically the data's center of gravity. If you could imagine your data's histogram as a solid object, like a piece of wood, the mean is the exact point where you could place a fulcrum underneath and it would balance perfectly. And you know the drill here. Add up all the values, divide by how many there are. Simple, easy. But it's the essential starting point for pretty much any analysis. Next up, the second moment, variance. This tells us how spread out or dispersed the data is from that central mean we just found. So a really small variance means all your data is bunched up tightly around the average. A large variance, that means your data is scattered all over the place. Now hang on, because here's a super important detail that trips a lot of people up. The difference between population and sample variance. See, if you have data for the entire group you're studying, the whole population, you divide by n. But let's be real, we almost never have that. We usually just have a smaller sample. In that case, we have to divide by n-1. It's called Bessel's correction, and while it might look a little weird, it gives us a way more accurate, unbiased guess of what the true population's variance is. It's a fundamental concept. You've got to know. Okay, so we've found the center, and we've measured the spread. Now we can ask a more interesting question. Is our data balanced? And that brings us to the third moment, skewness. This is all about measuring the lopsidedness of our data. Skewness basically puts a number on how much a distribution leans to one side or the other. A perfectly symmetrical distribution, like that classic bell curve, has a skewness of 0. But real-world data? It's rarely that neat and tidy. And it really just boils down to this. A positive skew means you have a long tail on the right, stretched out by a few really high values. The classic example is income data. A handful of billionaires will pull the average way up. A negative skew is just the opposite. The left tail is longer, dragged down by some super low values that pull the average down with them. And this QQ plot shows it perfectly. See that straight line? That represents a perfectly normal, symmetrical distribution. But look at our data points. See how they curve up and away from the line at the top? That's telling us that the values in our data's upper tail are way higher than we'd expect, which is the classic signature of a right-skewed data set. Alright, now for the main event, the fourth moment, kurtosis. This is where we go beyond all those familiar measures to really understand the extremes of our data. We're talking about the outliers and the tails. So kurtosis is the fourth standardized moment, and its entire job is to measure the tailedness of a distribution. Now listen closely, I said tailedness, not peakedness. This is a huge point of confusion, and it's probably the number one thing people get wrong about kurtosis, so we're going to clear it up right now. Now, let's not get lost in the math here, but the idea behind the formula is actually really powerful. It takes how far each data point is from the mean and raises it to the fourth power. Just think about that for a second. A point that's, say, 2 units away from the mean contributes 16 to the total, but an outlier that's 10 units away, it contributes 10,000. This is exactly why kurtosis is all about the extremes. The data points near the middle barely even make a dent. So let's lock this in. If you remember one thing from this whole explainer about kurtosis, please make it this. Kurtosis measures the tails, not the peak. And hey, don't just take my word for it. This quote from the statistician Peter Westphal says it perfectly. Kurtosis is a measure of outliers. The data points near the center contribute almost nothing. The entire story of kurtosis is written out there in the extreme ends of the distribution. Okay, so to make this way more practical, analysts almost always use something called excess kurtosis. It turns out that a perfect normal bell curve has a kurtosis of exactly 3. So to make our lives easier, we just subtract 3 from whatever our result is. This makes the normal distribution our new zero baseline, and it becomes incredibly easy to see if our data has fatter tails or thinner tails than normal. And this gives us 3 really handy labels. If your excess kurtosis is positive, we call the distribution leptokurtic. The easy way to remember it is leaping. It has fat tails and a much higher chance of extreme leaping outliers. If it's 0, it's mesokurtic. That's our normal baseline. And if it's negative, it's plateaukurtic. Think flat, like a plateau. It has thin tails, meaning extreme outliers are actually less likely than in a normal distribution. So what's the bottom line here? Why should you care? Because kurtosis is your statistical smoke alarm. A high kurtosis value is a massive red flag screaming at you that you have extreme, impactful outliers you need to investigate. In finance, this concept of fat tails or high kurtosis is a critical warning sign for risk. It tells you that catastrophic market events are way more likely than your standard models might be predicting. It is the ultimate reality check for your data. And that's really it. When you put them all together, the mean, variance, skewness, and kurtosis, they don't just give you a bunch of numbers. They tell a story. They describe the center, the spread, the tilt, and the likelihood of surprises in your data. They give you a truly complete picture of its shape and its behavior. So the next time you're looking at a data set, please don't just stop at the average. Go deeper. Ask about its shape, its skew, and its tails. The first 4 moments can reveal an absolutely incredible story, but they always lead to a new question. What other hidden patterns are just waiting to be discovered?